Once you know how to calculate the short distance d, then you just go ahead to use the magnitude of the force multiply the short distance d. And then you multiply these two parameters together. And then you're going to decide whether you want to write the positive sign in front or you want to write the negative sign in the front. Positive sign means if you can identify it is a counterclockwise case, or negative sign indicating it is going to be the clockwise case. Okay, so that is pretty much the easy way to figure out two-dimensional moment calculation. But sometimes you do have a challenge to calculate the short distance, including myself. Sometimes it may not be easy for me to figure out the short distance. Then no problem either. If that's the case, I would like to suggest you to go back to use this equation. Okay, to go use this equation, because two-dimensional case is the special case of three-dimensional cases, right? In other words, the coefficient in front of k is equal to 0. That's simple, in fact, right? And then the coefficient in z direction of the force equals 0. And you still use the traditional r cross f to solve the problem. If you use this one, then you can ignore how you are going to calculate d, in fact. It's very simple, but it probably takes a longer time, right? So that's why for two-dimensional problem, you need to first ask yourself, is it straightforward for me to calculate, to evaluate the short distance d? And if the answer is yes, go ahead and use this one. If the answer is no, which is normal, okay? So then you go back to use the traditional equation, okay? So going back to talk about three-dimensional cases, how are we going to do the calculation using the cross product between r vector and the force vector? There's many ways. Either you can use this one. The first row is always ijk, fixed. The second row, three components. The second row, three components are the, this is not typical x, y, z, by the way, right? These are the three coefficients from r vector, okay? Because we assume r vector having these three coefficients, right? So we put in here. And the third row are the three components from the force vector. But then you need to know how to calculate the determinant of this 3 by 3 matrix. Okay? So don't just leave here. But leave here is better than writing nothing. Because if you write this one, and if you do not know how to write the details, at least you get some partial credit, right? If you do not write anything, this one we have to assume you even do not know how to, in principle, how to calculate the moment in three-dimensional setting. So back to the two-dimensional, this one should be 0, this one should be 0. Okay, there's even more general case. Instead of calculating the moment of a force about the original point, you can calculate the moment of this force about another point, B. Okay. So that is the first type of moment. We call the moment of force about a given point. The second type of moment is called the moment of force about a given axis. In order to calculate the moment of an arbitrary force vector about another arbitrary given axis, what you need to do is to follow this equation. Let me show you that equation. This one. So this is a moment of a force F about a given axis with a unit vector called lambda. So basically, you need to first, let me give a more general one. This is the more general one, right? So this is the equation for us to calculate the moment of a force about a given axis. So what you need to do is to randomly pick a point in this given axis. Any point you like. You want to pick point C, no problem. You want to pick point B, it's not a problem either. So then, once you pick point B, then you can evaluate this R, which is the distance vector from the point you just picked to the point the force is applied on. So this R, distance vector, is from B to A. It's from B to A, you're going to use A subtract B. Okay, so don't forget, use A subtract B. So this is called R, and then cross product with this force vector. Again, how to calculate the force vector? That's from chapter 2, which is the magnitude of the force multiplied with another lambda, which is the unit vector in that force direction. So after you do the cross product between these two vectors, and don't forget to have another dot product with this lambda. This lambda is the unit vector in this given axis. So this lambda calculation procedure is to randomly pick 2 points, and you can use the C subtract B or B subtract C, doesn't matter, because this given axis doesn't have a preferred direction. And that's the only exception, right? So typically when we talk about force, we definitely give you a preferred direction. So in other words, you have to calculate the lambda with the force direction correctly. But the only exception for this so-called given axis, you can use a B subtract C or use C subtract B, doesn't matter. Your final answer either positive or negative, that's okay. Okay, if you go back to recall the first midterm we had, right? Okay, that's the second kind of moment. The third type of moment is called a moment due to a couple or moment of a couple. And this is a very important concept because we frequently use this. You may not have the real situation like this, but this is the concept we frequently use in order to move one force to another one. And this is also the basis for us to calculate what we call the single force system in two-dimensional or three-dimensional problem. So by definition, the couple is to have two forces vectors which are parallel but in opposite direction, and they should have the same magnitude. So once you have this kind of special arrangement forming a couple, then you can calculate the moment due to these two special forces by picking any point you like, because the final result will be independent from the point you chose. For example, finally you get the moment due to this couple or due to these two forces, you finally end up with this equation. And this is in fact the universal equation to calculate three-dimensional moment due to a couple. In other words, you need to identify R, you need to identify F. So let's say if you identify F like this, you random pick any one of this as F. If you pick this F, then R is from any point another force line to any point on this force line. So that's why you call this R from B to A. From B to A, that means A subtract B, and then cross with this force vector. Okay? For two-dimensional problems, you can again use this one if you have a hard time to identify the short distance. If you can easily find out the short distance, then you can go ahead to use F times D. That's another simple way to evaluate the two-dimensional moment due to a couple. And then, of course, this is not enough. You need to also indicate the direction, whether it's clockwise or counterclockwise. That's the third kind of moment. The reason we keep talking about the moment due to a couple is because once we have such concept, we can move a force from one point to another one. And this is always the illustration I would like to use. For example, if you have a force acting on point A, for whatever reason you want to move this force at point A to point O, what you're going to do is you virtually add two forces in this direction. The reason I'm saying virtually adding these two because these two are canceling each other no matter what. Then from this negative F and this F, you can see these two special forces satisfy all the requirement with the definition of a couple. Then you are erasing these two forces, this force, not this force, and this one. Once you erase, then immediately you're going to add a moment. That's called equivalence, right? So when you erase something, you need to give equivalence. So then finally you end up with this force left here, but you have another moment. But the bottom line is from this finally to here, you'll find out we finish the requirement by moving a force from point A to finally point O. The reason I'm saying moving a force because you see the final force, this one, is identical with this, just at different locations. But you have to compensate the process by adding this moment. And how to calculate this moment? This is the moment due to a couple of these two. So basically it's R cross F. So that means that's the point you want to move the force to the point the original force applied. That's called the R vector, and then cross F vector. For two-dimensional problems, you just need to find the short distance. If you cannot, you can still use R cross F in three-dimensional setting as well. Okay? So once we understand such concept, which is called the moment due to a couple, then actually we can move a lot of forces into a certain location. And that is finally end up with the resultant force and the resultant moment. So the resultant force is simply adding all forces in different locations together to get the resultant force. And then the resultant moment is simply the summation of each R cross each F. and add them together. And that's called the resultant moment. So no matter how complicated the rigid body with multiple forces is, you finally end up with one resultant force and one resultant moment. You may say, well, that's not a big deal. For this case, originally you have 3 forces. You finally end up with 2 vectors. This maybe have the same kind of difficulty like this. I agree. But how about if you have a lot of forces, like 100 forces, for example, you still finally end up with 2 vectors. That's a much more simplified scenario. So that's why this is what we call force-coupled system. So if you gave multiple forces, multiple moment together, you just need to calculate resultant force, resultant moment, and then you say this is the equivalent force-coupled system. Force-coupled system. As a special case, if we talk about 2-dimensional force-coupled system, we have another concept which is called a single force system. So typically we call the certain system force-coupled system or force-moment system. That means you have one force and have one moment in the system. But for 2-dimensional problem, you can always find some point so that you can move all the forces to that point, and then the resultant moment happen to be 0. Using that concept, you can find out that location. Okay? For example, there is a rigid body like this. You have 4 forces acting on different locations, right? So then they may ask you to find out a single force system. The location at where, when you move all the forces to that point, and then the resultant moment happen to be 0. So how to solve such problem? So typically, you just need to randomly pick a point. Okay, you randomly pick a point. For example, you pick point A, or you pick point B, or you can pick this point, or you pick this point. No matter what, you move all the forces to that point. And then you finally end up with one force and one moment. And that force is called the resultant force, and that moment is called the resultant moment. So you simplify the original scenario with multiple forces into a single force and a single moment. And then you are going to assume at a certain point, like this point, and then you identify, where's my, well, I did not plot, right? Yeah, I think at that time I was used the projection to solve part C. This one. You first randomly pick a point, for example, pick point A or pick point B, any point you like, and then you can add all forces together, you get a single force, and you can calculate the resultant moment due to these forces, and this is equivalent to this. So then, the next step, you want to assume a point like this point, you don't know, then you can say from this point A to here, it's called X. That's a location to be determined, and then you move this one again to this point, and then you force the total moment equals 0 to calculate X. And if you can find the X, which is the solution based on this requirement, then you can conclude by saying if you move all the forces to this point, and then the resultant moment equals 0. And that's called a single force system. Okay? So that is chapter 3. Any questions? But such single force system typically occurs for 2-dimensional problem only. There's not easy to find a certain location for 3-dimensional problem. So that's why I never talk about 3-dimensional problem for the single force system. For example, like this question, right? That's the single force system, but at that time, there's only the 2-dimensional problem. Any questions? Okay, so now we move to the key part, which is chapter 4. Chapter 4 is the key for this class, but actually it's very straightforward because basically we talk about 2 cases, right? One is a 2-dimensional case, one is a 3-dimensional case. For 2-dimensional case, for 3-dimensional case, we'll talk about this first, okay? For 3-dimensional case, you finally end up with the 6 equations. But I don't want you to just simply write those 6 equations. Instead, I would like you to follow these 2 equations. These are 2 vector equations, but they are together equivalent to this 6 equation. Because this is a vector equation, you finally end up with 3 equations. And this vector moment equation, you finally end up with another 3 equations. Okay? For 2-dimensional problems, we finally end up with 3 equations. because among these, this and this are independent. This is the trivial equation. And then you basically collect the equation in terms of z-axis by picking any point you like. So these three equations are the independent equations. All the other three are dependent or trivial equations. Okay? You need to know the typical supports for two-dimensional problems. And the most typically used support we have is called a pin. Where's the pin? This one. This pin, right? This is the original way to plot a pin very carefully, but typically if you look at those examples, we plot a simple way as a pin, as you can see later on. Sometimes we deal with a fixed support. Okay, we deal with a fixed support. With a fixed support, you basically have three unknowns: the resistance in x direction, resistance in y direction, and then the moment resistance. For the pin, you basically have these two. And as another special case, if we talk about rocker and rollers, we basically have only one reactions. There's many cases we talk about short cable or short links. Basically, the force when you cut, that should follow that direction. Okay? So this is the example I talk about in terms of cables. There's multiple ways you can cut. But no matter what, after you cut, you need to plot those forces correctly. I'm not saying you cannot cut here. You can cut here, it's not a problem, but you need to give forces appropriately. So that's why this is correct. Just in case you want to cut here, no problem. The reason I'm saying that, if you go back to look at your second midterm, right? There's one question, something related with this. Okay? So if you want to cut here, you need to give two forces. The reason you give two forces is because both point B and point D are part of the rigid body. And if that's the case, you really do not need to cut. But if you really want to cut, then no problem, you gave the forces correctly. But the reason this one, you cut this cable, you only gave one force, is because the other side is connected with the foundation. And you are not putting the foundation as part of rigid body. And that's the concept you have to understand in order to cut the cable. Okay, so for those of you who have questions, I would suggest you to look at the details about this example. So again, this is a typical three individual equations. We have the summation of all forces in x direction, y direction, and then you pick a point and to collect the moment. So these are the typical three equations. And for many problems, in fact almost all problems, I really do not want you to do a fancy way to solve the problem. There's no competition between one student solving the problem in 10 minutes with another student solving the problem in 15 minutes. That's not the issue. The issue is you need to solve it correctly. I really do not care you submit your papers just in 10 minutes or half of the time. Of course, if you submit, it's no problem. But more important, I want to make sure you solve those problems correctly. And many times for those students who submit their papers early, it doesn't mean they get a higher score than you. So you need to make sure you check all the steps and to get those answers correctly. And then once you're confident, you can submit. Okay, we gave you enough time. That means you want to take advantage of those time. You really do not have to rush. There's really no rush. If you are the first student turn your paper, it doesn't mean I give you extra credit, right? So that's really no need. Okay, so that's the chapter 4. We also have a 2 force body and 3 force body problem. That's really up to you whether you want to understand it or not, because if you want to use component method, you can solve such problem very easily instead of knowing such concept. And of course, we finally have the 3-dimensional cases. For 3-dimensional cases, typically you just need to know you have a 6 equations. But I'm not going really asking you to write down those 6 equations, because if I really gave you a 3-dimensional static problem from chapter 4, it's going to take an hour to solve. So I don't want you to spend an hour to solve one problem. Okay, so that's why I'm not going to ask you any 3-dimensional statics problem from chapter 4.